get started today. Before we begin the chemistry part, Before we begin chemistry, I've been asked to announce another general meeting for the Pre-Veterinary Society. There's going to be a veterinary chiropractor there, a job that I did not know even existed, so that could be interesting. And that's going to be Thursday, February, I guess it was yesterday, so too late. They just sent it to me yesterday. I don't have class tomorrow, so alright, sorry about that. Forget I said that, but that is just a general advertisement for the PVSA if you're interested. Okay, we're going to talk today about Section 4.3. Before I get started, remember that I'll be holding an exam review this very location at 3 p.m. Today, so if you're able to come, please do. It could be helpful. It will be recorded and put on YouTube, and the problems that we go over, I'll post the solutions and everything on Blackboard, so you'll be able to catch up if you're not available. Another thing about the exam, it starts Mondays, so make sure you know what time you're supposed to go, and all of you go to the right location, which is the classroom business building. And just as a reminder, we will have class during exam week, so we don't skip out just because there's an exam. I will not be doing any bonus quizzes during the days of the exams in case you were forced to schedule your exam during class. I don't want to punish you for missing it for that. And then finally, the homework assignments are continuous regardless of whether there's an exam or not. So there will be a homework assignment due this Sunday, which I believe is still Chapter 3, so stuff that's related to the exam. But then the Sunday after the exam is going to be the first Chapter 4 homework, so make sure you don't forget about that in your euphoria about how you did in the exam. There still is homework to do. Okay, so today we're going to talk about a topic called hybridization. And so we're moving forward with some of the theories that describe the bonding in covalent compounds. We've now talked about the last two lectures, the three-dimensional structures of covalent compounds, and then some of the properties that result from that, primarily the polarity. And now we're going to talk about how do the actual atoms bond together in these compounds, and how do they make these different shapes that we've talked about. So for simple diatomic molecules, one way to think about the bonding is just overlap of atomic orbitals. So we know that each atom has certain atomic orbitals that are filled in the ground state, and then those orbitals can come together and overlap to form bonds. So the simplest one is H2. We know that H2 has a 1s1 configuration. We also know that the 1s orbital is spherical in shape. So for each hydrogen atom, you have a 1s orbital with a single electron in it. So you take two of these, you bring them together, and then probably the simplest idea about how chemical bonds work, which was really the early theories on bonding, was just that you had these two orbitals overlapping. Now, in this localized bonding approach that we're talking about today, which is referred to as valence bond theory, really the idea is that you still have two separate atomic orbitals, one on each hydrogen atom, but those orbitals are now overlapped when you bring those nuclei close together. So you get a picture that looks something like this, where you have one of the 1s orbitals on hydrogen overlapping with the other 1s orbital. And to make H2, you have the nuclei sort of in the centers of each of those, and then the two electrons that come from each hydrogen atom sort of reside in that overlap region, and that's responsible for holding the two nuclei together. So that's a pretty simple picture of bonding, which is just that atomic orbitals overlap and make the bonds that way. We can do it for more complicated atoms as well. So Cl2, we know that the configuration of each chlorine atom is going to be a valence configuration of 3s2, 3p5. Whenever we're talking about bonding, we only care about the valence electrons, in case that's not obvious by now. So the valence electrons for chlorine are 3s2, 3p5. The 3s orbitals are filled, so we can't really overlap those and put electrons into there because you can't have more than two electrons in an orbital. So because the 3s is filled, we'll use the 3p orbitals to overlap. And that 3p is going to have an unpaired electron, which we can then couple to form a bond. So we know that one of the 3p orbitals is going to have an unpaired electron in it, and so you're going to have, again, two 3p orbitals, one on each chlorine. And remember, the p orbitals have this sort of dumbbell shape with two different lows with two different phases. But if you take two of these and bring them together, Again, you're going to overlap the two orbitals. And you can have your electrons residing in that overlap region there. That's where the electrons go, and that's responsible then for the covalent bond between the two chlorines. So again, two localized, in this case 3p valence orbitals that can overlap to form a bond. So you're going to take valence orbitals, overlap them, but still in the valence bond theory you have each atom still has its own atomic orbital that's participating in that bond. That's going to be a key distinction to what we talk about next week with regards to that. And then finally we can do it for heteroatomic. So if the two atoms that form the bond have different valence orbitals, you can still overlap those two different valence orbitals. So as we saw, hydrogen is 1s1, chlorine is 3s2, 3p5. And so what we can do in this case is take the 1s orbital on hydrogen, and then the 3p orbital on chlorine, and we can overlap two different orbitals to form a bond, where again it's just two atomic orbitals coming together to form a bond. The electrons sort of go in that overlap region, and so you have a 1s 3p overlap to make HCl. Okay? Alright, so that's sort of the simplest picture of bonding for very simple diatomic molecules. You can just think of atomic orbitals coming together and overlapping. Now, as we'll see later on, this is not a sufficiently accurate theory to describe everything, so we have to introduce a more complex bonding theory later. But the other piece of this that we should realize is that we can't use this simplified atomic orbital approach for every single molecule, because when we start talking about more complex geometries, it just doesn't work out. So let's get into that now. So we're going to have what's called hybridization, where we're going to mix atomic orbitals on the central atom to make new orbitals that are then going to be involved in the bonding. So let's look at the molecule BeCl2 and focus in on the electron configuration of the central atom. Now, if we drew the Lewis structure for BeCl2, we would predict a linear geometry. So using VSEPR, we predict this as linear. And how do we get then two different bonds forming that are 180 degrees apart from each other using only atomic orbitals? That's not really possible to do. And if the other thing we look at too is that beryllium, the central atom, has a valence configuration of 2s2. So it has a filled 2s subshell and then empty 2p orbitals. And as we talked about, when you're forming covalent bonds using this simplified approach, you typically need to have unpaired electrons that come together and overlap in those orbitals to form bonds. And here we don't have any unpaired electrons. Furthermore, it's a 2s orbital, so how do you form two different bonds involving just a single spherical 2s orbital? And so this is where we have to invoke hybridization. So what happens then is, instead of using this pure 2s atomic orbital to form a bond, we're going to do what's called hybridization. And that's where we mix the valence orbitals on the central atom, in this case an s and a p. We mix those together, and we get what's called an sp hybrid orbital, or a set of two sp hybrid orbitals, and then we leave two of the p orbitals alone. So we're only taking this s orbital and then one of these three p orbitals, mixing them together, and then we leave the other two orbitals unchanged. All right, so the energy for our sp hybrids is between that of s and p, because it's a mixture of the two. The energy of our 2p is unchanged. This is our energy scale going bottom to top. And now when we take the two valence electrons on beryllium and add them to this set of hybridized orbitals, we get a situation where, following Aufbau principle and Hund's rule, we fill the two bottom orbitals here with one electron each. Now we have two unpaired electrons that are available to form the two bonds to the chlorine that are in BeCl2. All right, so the way this works then in a pictorial sense, this is sort of an energy level diagram. And I should point out that, this level, what I'm showing you guys here is a way to help you understand how this happens. In reality, the problems are going to be not as complex as this, but we're trying to give you really the background of what's going on here. So as I said, we mix together these s and p orbitals, and we form two new orbitals, and what do they look like? So to look at the picture of this, for sp hybridization, we're taking an s orbital and a p orbital on the central atom. And in any of these bonding theories we're going to talk about, valence bond theory, today, and then we're going to get into molecular orbital theory next week. Whenever you're talking about bonding theories, the number of atomic orbitals you mix together has to equal the number of other orbitals that you form. So if we're mixing two atomic orbitals, an S and a P, we're going to form two hybrid orbitals that we call sp. And so they sort of have mixed character from the S and the P. So imagine that you superimpose the spherical S orbital on top of the P orbital, and you can do it in two different ways, and you get an sp orbital that's facing this way, and then you get another one that's oriented at 180 degrees to that. All right, so the math behind this is more complex than we'll get into, but basically you get two sp orbitals that are oriented 180 degrees apart when you mix an S and a P together. And those two sp orbitals then are going to be responsible for the bonding. So what you have in beryllium is that you have your central atom. It's going to have one of its sp orbitals facing this way. It's going to have another sp orbital facing the other way. And so you have two sp orbitals 180 degrees apart, and then those are going to overlap with the orbitals from the chlorine. So we're talking about BeCl2 here as this example. We'll show our sp orbitals in blue, and then our chlorine atomic orbitals, those valence p orbitals that have one electron in them, those are going to overlap here. So we have one of our chlorine P atomic orbitals. We have another chlorine atomic orbital in P. 3p atomic orbital over here. And they overlap with those sp hybrid orbitals to form the bonds that we have in the linear BeCl2. So the orbitals that are involved in the bonding on the central atom are no longer pure atomic orbitals. They're these sp orbitals, and they're going to overlap with the chlorine atomic orbitals to make those bonds. Now we should also recognize, this isn't so important for this molecule, but it is for other ones that have this type of hybridization. As I said before, we have two p orbitals on the beryllium that are untouched. We hybridized the S and one of the p's. We still have two p orbitals left over. So those are still going to be there at 90 degrees apart, but they're going to be unfilled. So we have a p orbital going sort of in each direction, perpendicular to the bond axis. All right, so we still have those unhybridized p orbitals that are there as well, but in this case they're not filled and they're not involved in the bonding at all, but they are still there. So we're showing the unhybridized p orbitals in red. That's sort of the color coding I'm using here. And then we still, of course, then we have our electrons that go in the overlap region for this valence bond approach. All right, so this is one example of hybridization. Let's go through then the rest of the geometries and see how this works. So let's talk about sp2 hybridization. So all of these hybridizations are talking about correlate with one of our electron group arrangements. So sp2 hybridization is correlated with a trigonal planar geometry. And if we stop and think for a second about a trigonal planar geometry, we talked about this before. You have 120 degree bond angles, right? All the bonds are arranged in a perfect triangle, 120 degrees apart. Remember sort of this structure here. And if we think about the atomic orbitals on the central atom, if we were to use pure atomic orbitals from the central atom, how could this possibly work? Because we have our central atom is going to have S and P valence orbitals. The P orbitals are oriented at 90 degrees from each other. So it would be impossible to make 120 degree bond angles if we were just using pure P atomic orbitals. We have the PX, the PY, and the PZ orbitals, but those would only give you 90 degree bond angles. Here we have 120 degrees. So this sort of also convinces us then that we need some sort of hybridization to generate new orbitals on the central atom that are oriented 120 degrees apart that are available to form the bonds with the outer atoms. So if we look at an example of this BF3, the valence configuration for boron is 2s2 and then 2p1. Again, energy going from bottom to top. And so that's the free boron atom. And then if we want to form bonds with 3 fluorines at 120 degrees apart, we have to hybridize those. And this time, since we're making 3 hybrid orbitals to form those 3 bonds, we need to hybridize 3 atomic orbitals. So we take our 2s and 2 of our 2p orbitals to hybridize them. So in this case, we're going to hybridize 2s, 2 of these 3 orbitals. That's going to give us a set of sp2 hybrids It's going to give us one 2p orbital that's left unperturbed, and we're going to be able to form then 3 bonds because the 3 valence electrons from boron are going to occupy these 3 hybrid orbitals, and they're going to be available to overlap with orbitals from the fluorine and make those 3 bonds. And that allows us then to form those 3 bonds equidistant apart. All right, so again, hybridization of orbitals on the central atom allows us to form these different geometries that we see from the VSCPR approach. Okay, so that's sp2 hybridization. And so qualitatively, the picture is pretty similar to what we saw before. So for sp2 hybridization, we take eventually, come on. All right, we take our s orbital, and then we're going to take 2 p orbitals. We have to take 2 of them, and then we're going to make 3 of these sp2 hybrids. So all the hybrid orbitals have sort of the same basic shape. This one, because we're using 2 p orbitals, is going to have more p character or more p shape to it as opposed to s, but the basic shapes are not all that different. But we're going to make 3 of these then because we're mixing 1 s and 2 p. We're mixing 3 orbitals. We make 3 of these. And the only difference here is that we have 3 that just differ in their orientation in space. And so what we get then for BF3 is we have 3 of these sp2 hybrid orbitals that are going to be at 120 degrees apart. And those are going to then overlap with the p orbitals from fluorine. This is going to be a little bit harder to draw, but we get. So we get overlap there. And so each of those is going to overlap with one of our fluorine p orbitals. And then we also have an unhybridized p orbital on boron. We only use 2 of the p orbitals to form the hybrid orbitals. So there's one more left that's going to be perpendicular to the plane of the trigonal plane, and 3 other hybrid orbitals. This, again, in this case, this 2p orbital is empty and not involved in bonding. When we start talking about double and triple bonds, though, we'll see that these empty p orbitals, these unhybridized p orbitals, are important for forming multiple bonds. That's something we'll see later on. All right, so that's sort of the story here. We have our sp2 orbitals shown in blue, which form a trigonal plane, and then those are going to overlap with unhybridized 2p orbitals. On the fluorine, there's also an unhybridized 2p orbital on boron that's uninvolved in bonding. All right? With, again, electrons residing in this overlap regions here responsible for those shared electron pairs that we call covalent bonds. All right, so this is a picture of sp2 hybridization, which correlates with the trigonal planar geometry. And now we're going to see a couple examples with sp3 hybridization. So sp3 hybridization is associated with the tetrahedral electron group arrangement. So what we see in this is that each of these basic electron group arrangements, linear, trigonal, planar, tetrahedral, and then we'll show the other ones later, they all have a specific hybridization associated with them, where the central atom is going to hybridize its atomic orbitals in that way to be able to form those respective geometries. So the classic example for tetrahedral sp3 hybridization is CH4. And the carbon is going to be our central atom, and its valence configuration is 2s2, 2p2. And again, to reiterate the point I told before about why we need to have hybridization is that if we were just going to use the atomic orbitals on carbon to form bonds, we only have 2 unpaired electrons, but we know we're making 4 bonds. And these 2 unpaired electrons reside in orbitals that are 90 degrees apart, but the bonds in CH4 are 109.5 degrees apart. So again, we have to do something with those orbitals on the central atom to account for the ability to form bonds that are at a much different angle, and to have 4 of those bonds in this molecule. So we're going to hybridize all of the orbitals in this case. All of the valence orbitals are going to hybridize. The 2s and all 3 2p's are going to hybridize. And they're going to make a set of degenerate sp3 hybrid orbitals. So all 4 of these sp3 hybrids are at the same energy, and now our 4 valence electrons, we can occupy 1 in each and those are going to now be available to form the 4 bonds that we have in CH4. Okay? So we have 4 orbitals with equal energy, and that's responsible then for forming the 4 bonds of the tetrahedral CH4 molecule. Okay? Alright, so that's how sp3 hybridization works. And again, the picture of this is going to be very similar to sp2, it's just that the orientation of the orbitals is now tetrahedral 109.5 degrees as opposed to trigonal planar. So for sp3 hybridization, we take our s orbital, we take all of our p orbitals, all 3 of our p orbitals. Again, their orientations would be different as atomic orbitals, but we're just showing them like this, and then those all mix together to make a set of 4 sp3 hybrid orbitals. And again, they have sort of a shape that's in between an s and a p orbital, so you get sort of this asymmetric dumbbell shape, if you want to think about it that way, which is called an sp3 hybrid. The shapes are qualitatively similar to the other sp and sp2 hybrids, just slightly different because of the increased p character. And there's going to be then 4 of these that are identical but just oriented differently around the central atom. Alright, so then those 4 sp3 hybrids, this is a little bit harder to draw because it's now 3-dimensional, but we have our 4 sp3 hybrids that are arranged in a sort of a tetrahedral fashion. And if we're making CH4, they're going to overlap with the s atomic orbitals on hydrogen. So we have a hydrogen with its 1 s atomic orbital overlapping at each of those hybrid orbitals. And we have 2 electrons in each of those overlap regions that are responsible for the bonding in this molecule. Alright, so it's a little bit harder to draw because it's 3-dimensional. But the other key point is that in this case, because we've used all 3 of our p orbitals to form the hybrid orbitals, we don't have any unhybridized p orbitals left on the central atom. All of them are now involved in the bonding when we have a tetrahedral sp3 arrangement. Now, as I've kind of already alluded to, each of these hybridizations corresponds to an electron group arrangement, not necessarily to a specific geometry. So what happens if we have lone pairs in our molecule? How does that work with hybridization? So the key point is that hybridization correlates with electron group arrangement, not with molecular shape. Alright, so if we have ammonia NH3, and we were to draw the Lewis structure for this, we would get this picture here with a lone pair in our central atom now. We haven't talked about lone pairs yet in the context of hybridization. This is an AX3E structure, and because there are still 4 total electron groups, 3 X's and 1 E, 3 atoms and 1 lone pair, this is still going to be a tetrahedral electron group arrangement. Alright, so it's tetrahedral electron group arrangement, but this case what we have is our nitrogen has a valence configuration of 2s2, oops, I labeled that in the wrong spot, 2s2, and then 2p3. Alright, the valence orbitals on the central atom are still arranged in a tetrahedral fashion. It's a tetrahedral electron group arrangement where one of those positions is now a lone pair, the other 3 are atoms. And so we're still going to do sp3 hybridization. Anytime we have a tetrahedral electron group arrangement, whether it's AX4, AX3E, AX2E2, as long as there's 4 total electron groups, you will do sp3 hybridization. And so what we get then is still the same picture before, where we hybridize all of our s and p orbitals to make a set of sp3 hybrids. But this time we have 5 valence electrons on our central atom, 2s2, 2p3. So when we fill these hybrid orbitals, what we get is 1, 2, 3, 4, 5 electrons. These ones are paired up. This is going to be our lone pair. So one of the sp3 hybrid orbitals has the lone pair in it, and then the other 3 sp3 hybrid orbitals are going to be available to form the 3 bonds that we have in NH3. All right, so it's really no different than the example for CH4, but in this case, one of our hybrid orbitals has a lone pair, and there's only 3 then that are involved in forming bonds with the hydrogen atoms. All right, so the key point is that hybridization correlates with electron group arrangement, so if you have lone pairs, they will also reside in those hybrid orbitals. Okay? We have 2 more types of hybridization to talk about. The pictures for these are a little more complicated, so I won't even attempt to draw them, but we should understand how it works. Now, I'll give the caveat that I always give at this point, which is that this type of hybridization that involves d orbitals, when we're talking about 2 hybridizations that involve d orbitals, there's much debate in the community about whether d orbitals are actually involved in bonding or not for main group elements, and I think most people think they're actually not. So we're kind of, in some sense, lying to you at this stage and telling you that d orbitals are involved in hybridization when they're really not. But it's a good way to think about it and a good way to rationalize the structures, even if it's not 100% rigorously correct theoretically. So just be aware of that if you take a chemistry course later on and they start teaching you that d orbitals are not involved in hybridization. It's not that I've deliberately lied to you. I'm well aware of that fact, and I'm not trying to pull the hood over your eyes, but this is how we describe it in a general chemistry context, and it still is useful for rationalizing the structures that we see for some of these compounds. So if we go beyond 8 valence electrons, so we saw that there are many Lewis structures where we had more than 4 pairs of electrons around the central atom. We obviously then have to have more than 4 orbitals that are involved in forming those structures, and this is where the d orbitals get involved. So this is only going to happen if we're in the 3rd row or below in our p block. All right, so these are the elements that can expand their octet. Only when they can expand their octet can we actually invoke more than 4 electron pairs around the central atom. And also, remember that when we're in the 3rd row and below, if we're in the 3rd period, we do have 3 d orbitals that are available. Even though they're not filled in the ground state, there are d orbitals in the 3rd shell that are relatively close in energy. If you're in the 2nd row of the periodic table where you're 2s and 2p, you don't have a set of d orbitals that's close in energy to hybridize. So it's really only for these heavier atoms in the 3rd row or below that we actually would invoke this type of hybridization. So the first one we're going to talk about is sp3d. I think your book calls it dsp3, but it's the same thing. It's 1 d orbital, 1 s orbital, and 3 p orbitals. dsp3 or sp3d. And this correlates then with the trigonal bipyramidal electron group arrangement. So an example of this is PCl5, which is AX5. In this case, all 5 of those are going to be involved in bonding. And so what we have here is if we want to form 5 bonds to our central atom, we can't just use the s and the p orbital. So we have our 3s and 3p ground state. So our phosphorus is our central atom. It's going to be 3s2, 3p3. But if we want to form 5 bonds, we can't just use the s and p orbitals. We also can't just use the pure p orbitals because there's only 3 unpaired electrons. So in this case, we're going to mix in some of our 3d orbitals as well, which are empty in the ground state, but they're close enough in energy that we can mix them with the 3s and the 3p. Or at least that's how it was believed to be for a while, whether that's actually true or not. But anyway, if we do this sort of hybridization where we have 3s, 3p, and 3d, we get a set of sp3d hybrids. There are 5 of them because we're mixing 5 orbitals together, an s, 3 p's, and a d. And now we have singly filled sp3d hybrids, 5 unpaired electrons that can then form the 5 bonds with the outer atoms. And then we leave the other 3d orbitals alone, so there's still going to be 4 unhybridized 3d orbitals, which in this case won't participate at all in anything. Alright, but because we have 5 degenerate orbitals, each with a single electron in them, we're now able to form 5 bonds. And if we had extra valence electrons, such that one of these was a lone pair, we could also put lone pairs in those orbitals if we were forming the seesaw geometry or the T-shaped geometry where you have 5 electron groups with 1 or more lone pairs. Alright, so this is sp3d hybridization, and it correlates directly with the trigonal bipyramidal electron group arrangement. And then the last one we'll talk about is sp3d2, where, as the name suggests, we're going to have 2 d orbitals involved in the hybridization. And again, your book, I think, might call this d2sp3. So there are 2 ways of denoting it, but they're the same thing, same exact thing. And this correlates then with the octahedral electron group arrangement. Example of this being SF6, which is AX6. All right, so if we look at sulfur as our central atom, sulfur has a filled 3s orbital, and then it's going to be 3p4. It's in group 6 of the periodic table. All right, so again, if we want to form 6 bonds to sulfur, we can't just use the 3p orbitals because there's only 2 unpaired electrons. We can't just mix the s and the p together because that would only give us a maximum of 4 bonds. So then we invoke the mixing in of some of those d orbitals as well, which are close enough in energy to mix in. So when we hybridize, in this case, we get a set of 6 equal sp3d2 hybrids. We leave the rest of the 3d orbitals alone. There's 3 unhybridized d orbitals still, because we've only used 2 of them to form the hybrids. And then what we have is 6 valence electrons that are going to then singly occupy each of these sp3d2 hybrid orbitals, and those 6 valence electrons in these 6 orbitals are going to overlap with orbitals from the outer atoms of fluorine to make the 6 bonds. Same picture as before. All right, so when we have an octahedral electron group arrangement, you're going to have sp3d2, where we invoke mixing in of 2 d orbitals. All right, so this is sort of the theoretical backdrop for how hybridization happens. Hopefully this helps you understand what's going on and why it has to occur. You know, the reasons why we even talk about this at all. But really the most important thing that you're going to have to be able to do on homework assignments and exams is look at a structure, look at a molecule, draw it out, draw the Lewis structure, and then be able to predict the hybridization. And that, whether you understand most or all these details or not, I think is a simpler thing to do, and there's a nice shortcut to be able to do this. And so what this relies on, as I've mentioned many times already, is the number of electron groups, or what I call the steric number. So you have to be able to get a good Lewis structure at the very least. If you're going to predict the hybridization of something, you need a Lewis structure where you have the correct number of valence electrons around the central atom, so there's no shortcut to avoid that. But if you know the number of electron groups, which we call the steric number, you can then instantly predict the hybridization. Okay? So if our steric number is 2, then we need to use the first 2 orbitals to hybridize. Remember that the available orbitals for hybridization are an s orbital, a set of 3 p orbitals, and then a set of 5 d orbitals. We're never going to use more than 2 of the d orbitals, but they're all there. So if we're going to make a steric number of 2, if our molecule has a steric number of 2, we need to use the first 2 orbitals for hybridization. So we circle the first 2, and that gives us sp hybridization, which correlates with the linear geometry. All right, so all you have to do is get the number of electron groups correct, and then you use that many orbitals to hybridize. So if our steric number is 3, if we have 3 electron groups, we then need to hybridize 3 orbitals. So we take the first 3 of these, an s and 2 of the p's. That gives us sp2, and that's going to be a trigonal planar electron group arrangement. Trigonal planar. All right? And then it goes on and on. So if our steric number is 4, we have to hybridize 4 orbitals. We take the first 4 of these, an s and 3 p's. That gives us sp3 hybridization and a tetrahedral arrangement. Steric number of 5, now we need to use 5 orbitals for hybridization. So 1, 2, 3, 4, 5, s, 3 p's and a d. We call that sp3d. And that's our trigonal bipyramidal. Electron group arrangement. And then finally, the highest what we'll go to is 6. We need 6 orbitals to hybridize. So 1, 2, 3, 4, 5, 6. That's going to be sp3d2. All right, and that's octahedral. All right, so once you have a good Lewis structure, again, all of these things rely on having a Lewis structure correct to begin with. Once you have the Lewis structure, you can predict the geometry as we talked about on Monday, and you can predict the hybridization using this trick here. And that's typically as deep as we're going to have you go when we're talking about hybridization. But there are some more details that we'll get into also later. So let's do just a couple more examples of how we would show this on homework assignments and exams. All right, so the first one is predict the hybridization of the central atom in COCl2. Carbon is the central atom. All right, so as I said, the first thing we need is a good Lewis structure, so we have to count valence electrons. Carbon has 4 valence electrons, Oxygen has 6. All right, so I'm going through this kind of fast because Lewis structure should be a review at this point. And then chlorine has 7 valence electrons. There's 2 of them, so we get a total of 14 from chlorine. So in total, we have 24 valence electrons in this molecule. All right, so when we draw the Lewis structure, we start with our central atom with single bonds, 1 oxygen, 2 chlorines. We complete the octets of the outer atoms first. All right, and that's all 24 of our electrons. We've used 8 on each outer atom. 8 times 3 is 24. So we don't have any more electrons to put on the central atom. Now, if we're going to draw the best Lewis structure for this, which doesn't matter so much if we're just trying to predict the geometry of the hybridization, but if we want to draw a better Lewis structure, we notice that our central atom only has 6 valence electrons right now. It only has 3 bonds, 2 electrons each for 6 electrons. So if we want to complete the octet of our central atom, we need to draw a double bond, and the double bond is going to go between the carbon and oxygen, because right now this oxygen has a -1 formal charge. So if we take off 2 of these electrons from oxygen and convert it into a double bond, we now have a complete octet on our central atom and no formal charges. All right, so that's an example where we have to use double bonds to complete the octet of the central atom, and then it also gets rid of a formal charge that we had to start with as well. So this is the best Lewis structure, but again, if you had forgotten that double bond, if all we're asking about is hybridization, it doesn't really matter. So all we have to do is count the number of electron groups attached to the central atom. And this is going to be an AX3 structure. And remember that we don't care if it's singular or double bonded. This counts as 1 electron group. So we have 1, 2, 3 atoms bonded to the central atom, no lone pairs. So if our steric number is 3, for carbon we have an s orbital and 3 p orbitals. We have to use 3 of those for hybridization to get a steric number of 3. And so our hybridization is going to be sp2. Okay? So anytime you have 3 electron groups, you're going to have sp2 hybridization. That's what we see here. All right, any questions on that? All right, so one other example, which you might see something like this on the practice test just for completing the Lewis structure, but then we're also going to talk about it in the context of hybridization. We have this skeleton structure here, and it says complete the Lewis structure and predict the hybridization of all of the carbon atoms in the following molecule. All right, so this is something kind of related to what you'll do in organic chemistry, but we have the tools now to do it ourselves. So you might see some of these on the exam as well, where we give you just a partial Lewis structure and you have to fill in the rest. So whenever we have these types of compounds that are mostly carbon, hydrogen, oxygen, nitrogen, these organic compounds as we call them, remember that the idea is that all of these atoms, except for the hydrogen, should have complete octets and ideally no formal charges. These are all neutral molecules. So there's sort of a shortcut we can use to make sure that the structure is complete when we have this type of arrangement. So most of these types of molecules where we give you these long extended chain structures are going to have just 4 main elements or 5 main elements in them. Okay, so hydrogen is obviously going to be a major component of these, and just like any other case, it's going to form 1 bond. So you never want to add any additional bonds or lone pairs to hydrogen. But for the rest of the atoms in this, the ones that are in the 2p part of the periodic table, we need to make sure again that their octets are complete and that they have no formal charges. Now you could do this the long way, which is to count up all the valence electrons in this molecule and then add in all the double bonds and things to minimize formal charge. That could take a while, so let's look at what the patterns that evolve then. So if you have a carbon atom in there, it's going to want to have 8 valence electrons, and those 8 valence electrons are going to be in the form of 4 bonds and 0 lone pairs. All right, so for carbon, you're almost never going to have lone pairs. It's always going to just be 4 bonds to carbon. So each carbon should have 4 bonds exactly. If you have nitrogen, which is 1 period over, again, it wants to have a complete octet, but to minimize formal charge, you're going to have 3 bonds and 1 lone pair. So this one doesn't have nitrogens, but if you had a nitrogen in your structure, you would try to make it have 3 bonds and 1 lone pair. If you have oxygen, it wants to have 2 of each, so 8 total electrons, but it's going to have 2 bonds and 2 lone pairs. And then if you have halogens in here, like fluorine, chlorine, bromine, iodine, these aren't as common in these types of structures, but they could be there. Those again are going to have 8 total electrons, but it's going to be 1 bond and 3 lone pairs to minimize formal charges. Alright, so this is what you want for one of these structures. You want carbon to have 4 bonds, nitrogen to have 3, oxygen to have 2, and then the rest of the octet made up by lone pairs when necessary. So if we look at this compound here, this first carbon atom has already 4 bonds. If we count the bonds, it has 3 bonds to hydrogen, 1 bond to the carbon next to it. So we don't do anything else to this. It already is happy with this 4 bonds. But if we go to this carbon here and we count, it only has 3 bonds, and the carbon next to it only has 3 bonds. So each of those carbons needs 1 more bond to have their full octet and to have exactly 4 bonds, so we can draw a double bond between them. Alright, so if we add a double bond there, that's going to give us a total of 8 valence electrons for each of those carbons, 4 bonds for each. We go to this carbon here, and it already has 4 bonds, 1, 2, 3, 4. So we don't add any more bonds to this one. But then if we go here, we see that this carbon has 3 bonds, and it wants to have 4. This oxygen has 1 bond, and it wants to have 2. So if we draw a double bond there, that's going to give us 4 bonds to this carbon, 2 bonds to this oxygen, and this oxygen should also have then 2 lone pairs to complete its octet. And then finally we go to these last 2 carbons here. Each of them only has 2 bonds at this point. 1, 2, 1, 2. So we need to have 2 more bonds for each of those, so that can be accomplished by drawing a triple bond. Okay? So you don't want to add any lone pairs to carbon, you just want to add in bonds until each one has exactly 4 bonds. And then if you have oxygen, nitrogen, or one of the halogens, you would then have lone pairs there. So this is how we complete the Lewis structure for this. And now we can go ahead and start predicting hybridization for each of these. So this carbon here, the first one, has 4 electron groups, has 4 bonds, 4 single bonds, 4 electron groups total. So it's going to be sp3 hybridized. These 2 carbons here are the same, as it turns out. So if we look at each of these 2 carbons, they have a total of 3 electron groups. They're bonded to 2 carbons and 1 hydrogen, a total of 3 electron groups on those carbons, and so they're going to be sp2 hybridized. This carbon here, 1, 2, 3, 4 electron groups, 4 single bonds, which means it has to be sp3 hybridized. Alright, this carbon here has 1, 2, 3 electron groups. It has a double bond. We only count that as 1 electron group. So if there are 3 things bonded to that carbon, it has to be sp2, 3 orbitals for hybridization. And then finally, these 2 here are also the same as each other. So if we look at each of these carbons, they each have 2 things bonded to it. This one is singly bonded to a carbon and triply bonded to the other carbon. This one is triply bonded here and singly bonded to a hydrogen. So each one is bonded to attached to 2 things, which makes it sp hybridization. Okay? Alright, so this is an example then where we have all the hybridization predicted for these, 1, 2, 3, 4, 5, 6 carbon, 7 carbon atoms, whatever it is. So if you can complete the Lewis structure, you can count the number of electron groups, that allows you to predict the hybridization for any atom in the structure very quickly. Alright, so you'll see some of that on the homework either this week or next, and for those of you that are available, I'll see you back here at 3 o'clock.